Sí, sí. So morning, everybody. Thank you for coming to the cycle of conference of the IQ. Today we have the pleasure to have with us Professor Jeremy Smith. He's a professor in the Department of Chemistry at Indiana University in USA. Professor Smith was raised in Benoni, South Africa. He was obtaining his PhD in organometallic chemistry at the University of Witwatersrand in Johannesburg. Then, after a couple of postdoctoral stays in USA, at Dartmouth College with Russell Hughes and the University of Rochester with Patrick Holland, he started an independent career in the University of New Mexico in 2003. 10 years later, he joined the University of Indiana as a professor in chemistry, where he's currently working at this moment. His research interests are centered in organic chemistry, organometallic catalysis, and also in electrocatalysis. So today, Professor is going to present a talk titled Atomic Ligands on Iron. It's a great pleasure to have you here today, and the floor is yours. Thank you.
All right, thank you for the introduction. It's really good to be here, and I really appreciate the kind hospitality and organizing my visit here. Yeah, sometimes I think it's tricky to arrange for someone who just says I want to come visit, but I really appreciate the hospitality and the chance to come and meet with people here. So I'm going to talk about a project that in some sense has been going on almost since I started my independent career in New Mexico, looking at metal ligand bonds really, and then we sort of focused on ligands that are only one element, but have just a single atom. So I'm not going to talk about iodide complexes, I'm going to talk about chloride complexes, for example, but where we have a metal ligand multiple bond to a single element. So why would be interested in this? Of course, there's fundamental reasons. Can we understand issues of structure and reactivity? Sometimes it's just a challenge. People say this cannot be made, but we think maybe that's not right. Maybe we can figure out how to make it, how to stabilize it. But beyond that, there's many examples of what I'm going to call atomic ligands in catalysis, both in biology and in industrially relevant catalysis. So, for example, the oxidation O2 is used as an oxidant in biology. There are many enzymes that do this, but for the iron-based enzymes, they often start out as iron 2, and then through multiple different pathways, eventually get to an iron 4 oxo. So this iron 4 oxo does a lot of oxidation chemistry. So there's examples of these in your body, for example, cytochrome P450s that metabolize drugs. So these are very important kinds of species with biological and health implications. The thing I want to note here is now we have a single atom, so oxygen here, with a multiple bond to iron. And so one of the reactions that they do is hydroxylation of CH bonds. So this mechanism, or the proposed mechanism for this, is that we have initially hydrogen atom transfer from a CH bond. This generates an iron 3 hydroxide, and then this rebounds to the radical that's remaining from the hydrocarbon substrate to oxidize the CH bond to an alcohol. Other types of examples of atomic ligands, so in the nitrogenase iron molybdenum cofactor, that's where nature reduces N2 to ammonium. There's a single carbon atom where there's quite a bit of debate going on as to what its role is. At least from our perspective, it's a single atom. Possibly there's some intermediates involved where this single atom is bound to a single iron atom from the enzyme. And then in industrial processes, Haber-Bosch catalysis converts nitrogen to ammonia. It's an incredibly important reaction for humanity's existence. But one of the intermediates then is there's surface nitrides that are formed from N2. Now these, I'll admit, are going to be different from the kinds of compounds I'll show you, because it's highly unlikely that this surface nitride is bound to a single ion atom, but nonetheless it's a single atom on the surface. And then in Fischer-Tropsch catalysis, which converts CO and H2 to hydrocarbons, likewise there are proposed surface carbide species. So by making molecular analogs of these kinds of species, we can understand some of the fundamental properties of these types of ligands. Possibly we could also go towards doing other kinds of catalysis in homogeneous reactions. So for homogeneous chemistry, nitrides can be formed or made from N2. So the original example was from Kit Cummins' group, where this 3-covalent molybdenum complex could cleave N2 to make this nitride, molybdenum nitride. And there's been a lot of work, particularly in the last 5 or 6 years, on this kind of idea. So, for example, Sven Schneider's made rhenium nitrides from N2, and they've been working on how to convert this nitrides into organic products. So, for example, Sven's group has shown you can make benzonitrile and benzamide with a nitrogen atom originates from N2. And then, as you can imagine, for the O2 systems, so there's been a huge amount of work making iron 4 oxos, and then understanding their fundamental reactivity to do oxidation chemistry of different substrates. And there's some examples even in using them for catalysis of more complex molecules that organic chemists might find interesting. Okay, so it's, I think, worth looking at where you expect to find a metal ligand bond in the periodic table as far as transition metal goes, and also why this is the case. So, quite a long time ago, this very famous paper from Harry Gray and Bollhausen looked at the electronic structure of vanadiol, so vanadium oxo. And so this is taken directly from their paper. And so what's really important here is these are the metal-based orbitals here, and the resulting molecular orbitals. We have this one set here, which if your z-axis is along the vanadium-oxygen bond, this is going to be the dxy orbital that's completely non-bonding. Every other orbital here has some anti-bonding character to the ligands. And notice that this E pi, so this is the pi star orbitals to the vanadium-oxygen bond, are the next highest. So in this case, if you have up to 2 d electrons in here, you can accommodate that without populating anti-bonding orbitals. But the moment you have 3 electrons or more, then you start to lower the bond order to that metal ligand multiple bond, and that leads to a lower stability. And that's why you see that, for example, if you just look at the crystal structure database, if you look at oxo complexes, you see them mainly for the middle of the transition metal series, similarly with nitrides, also mainly in the middle. Okay, admittedly, these are crystal structures, so it's not completely related to exactly the distribution, but I think it gives you a good sense of the stable types of metal ligand multiple bonds you see for these types of ligands. And this also suggests to us that these are so stable, you might have to work a lot harder to get these to do any sort of interesting reactivity than these kinds of complexes that are sort of on the extremities of stability, which are harder to make and stabilize, but then may potentially lead to more interesting or greater reactivity. Okay, so what's been shown for metal ligand bonds and specifically these atomic ligands, what kind of reactions could you do? So just for some hypothetical atomic ligand, you could do a CH insertion like I showed you for the iron 4 oxos to functionalize hydrocarbons. You can do atom transfer to different substrates, so you oxidize the substrate. Another reaction that is often seen or has been seen is metathesis, so exchange one atomic ligand for another ligand. And then you could also use these as precursors for making clusters in a well-defined or controllable fashion. So there's many things that you could do with these. And another thing I should point out is that it's possible to change the reactivity of this ligand here by playing with the other ligands on the metal. So for example, if your metal d orbitals are higher in energy than the frontier orbitals of the metal ligand multiple, or the multiple bonded ligand, then the HOMO is going to be weighted towards this element. This is going to make this more so that means that this will be nucleophilic ligand here. So we have the lone pair or electrons on the ligand. So this is typical for an early transition metal complex which have higher energy d orbitals. But in principle, you could change that by changing the other ligands on a later metal. Conversely, if you have a later metal or you lower the energy of the metal-based orbitals, then the LUMO is now weighted towards the elemental ligand, and this should be more electrophilic in character. Okay, so there's opportunity here to change the nature of the reactivity. Okay, so if we can't easily make a compound that has a metal ligand bond that's 6 coordinate, because we're going to populate metal ligand antibonding orbitals, how do we get around this? And the first demonstration of this that I'm aware of was shown way back in the late 80s, early 90s by Bob Bergman's group for iridium, where they made this very interesting molecule, this pogo-stick iridium, where they have a cyclopentadienyl ligand, and then we have this imido ligand here. And so this is iridium-3, because this is a 2- ligand, and since it's a third row element, it's a low-spin D6 complex. This is a perfectly stable molecule, has some really cool reactions. But what I wanted to point out here is that we've changed the symmetry at the metal here. So this is no longer pseudo, let's say, 6 coordinate. Well, it's not 6 coordinate for sure, but it's no longer pseudo-octahedral. It's more of a pseudo-tetrahedral geometry. And this, again, is taken from their paper. And so this is, I think, very simply just sort of back of the envelope type of calculations show that if, again, we define our principal axis along the metal ligand multiple bond, then we have the dxy, dx squared minus y squared orbitals that are now non-bonding with respect to this bond here. And then those are now filled with electrons. We also have this dz squared orbital, and I'll come back to that in a second, which is also not very strongly bonding. And then the pi symmetry orbitals, the pi star orbitals, are much higher in energy, and they're unoccupied. So we have a triple bond here that's composed of 1 sigma and 2 pi bonds. And this is now, as I said, D6, high D electron count for this type of compound, and it's a stable molecule. So that's a heavy element. If you now try to make something for a lighter element, so a 3D element, so now the ligand field splittings are not as large. You have to do a bit more work. These tend to be more reactive in some ways. But Klaus-Theopold showed that they could transiently make what they believed was this cobalt imido complex with a tris-perazyl borate ligand. So this is somewhat like a cyclopentadienyl ligand. And if they changed the R group from cidal to adamantyl, then they could actually isolate a compound that shows interesting spin crossover behavior. So again, changing the symmetry here changes the stability of the metal ligand multiple bond. And then in the early 2000s, Jonas Peters' group was able to show that if you use these tris-phosphenoborate ligands that are much stronger donors, then you can isolate and stabilize low-spin complexes with metal ligand multiple bonds and high D electron counts. So that was the strategy we want to approach or adopt, is to make metal ligand bonds. And so the idea is we'll use a different geometry or different symmetry at the metal that should allow us to get to higher oxidation states, and then we can stabilize these kinds of bonds with later metals. So if we want to look at now atomic ligands, so we don't have any steric protection like we did with an imido, there's no R group. So Jonas's group showed that you could transiently generate this iron nitride with this tris-phosphenoborate ligand. But because it's relatively exposed, so the isopropyl groups here, although they're big, they're sort of splayed away from the metal ion. They don't protect this very well. And then this complex could never be isolated as a nitride because when left to its own devices, or they try to concentrate it for crystallization, it almost always dimerized to make this N2 compound. So our thought, well, is that we need to change the topology here a little bit so that we prevent this coupling reaction from happening. And so we chose to use tris-carbene borate ligands. So they're somewhat like tris-perazyl borate ligands, which are very well studied. But the most important difference is that we now bind to the metal through a carbon atom from a stabilized carbene. These are very strong donor ligands. We can change the R groups here. We can learn a lot. We know a lot from the work that had been done with tris-perazyl borate ligands about what effect the R groups here on the properties of the metal, particularly the steric properties. And so we can make these ligands. And so just one example here, if we made an azide compound, we could fertilize it to make a nitride. We could actually crystallize this compound, store it in a bottle. We could look at its reactivity at our leisure. And we've done this with a bunch of different R groups here. And then in one case, we actually could oxidize this to an iron 5. and that's the crystal structure here. So this is a very nice platform for looking at these metal ligand multiple bonds. So these are all, as I said, thermally stable. These are also low spin. So this is iron 4, it's D4 low spin diamagnetic compound. We can get also like multi-nuclear NMR on this. Now, I'll just note that other groups have looked at this using similar strategies. I already mentioned Jonas Peters' group, but Carsten Meyer in Erlangen and Sky Fortier in Texas have also examples of iron nitrides using similar types of strategies or ligands. Okay, so let me just go back to this idea of change in symmetry just to hopefully drive home the point. So another way we could think about the bonding in compounds such as ours is to start with a well-known geometry, so a 5-coordinate trigonal bipyramidal structure, so D3H symmetry. So this would be the orbital mixing or the orbital splitting you write down for the d orbitals based on the symmetry here. So we have the lowest line orbitals are the dxy, dyz, which are actually along the z-axis here. Now, if we start to bend this angle here, which is 90 degrees in D3H, and we make this larger as we go to C3V, then what happens is that these two sets of orbitals here are no longer orthogonal, and they can mix. And so if you look at the orbitals that come out of this, that it looks like these two are going down in energy to form the lower line set here, and it looks like these two are going up in energy. But in reality, these are now mixed because they're not orthogonal anymore. So at about over 117 degrees, apparently you have the lower line orbitals as the x squared minus y squared and xy. So basically perpendicular to their principal axis. So the consequence for that is now we can put a lot of electrons in here that are not going to be along the z-axis. They're not going to affect our metal ligand multiple bond. So if we look at our iron 4 nitride compound here, so it's this kind of geometry. This is basically a just cartoon representation of what we found from electronic structure calculations. So the lowest line metal-based orbitals, all the electrons are essentially in the xy plane. So there's very little antibonding character. The next highest orbital, so the LUMO, looks like it should be antibonding because there's a dz squared orbital and then some sigma donor orbital from the ligand. But actually this orbital is mixed between dz squared s and p to make this SPD hybrid, and that reduces the antibonding character along the axis. Okay, so this allows us to now think about this as essentially a non-bonding orbital. In terms of reactivity, so we can put electrons in here without really compromising the metal ligand multiple bond. So this nitride should be somewhat electrophilic. We also have some electron density on the nitride ligand in the HOMO. So this also has some nucleophilic character, and that's what we've shown is that the reactivity is actually ambiphilic. And so this is really just a summary of some of the reactions we've seen. So the nitrides can do, for example, reactions with alkenes to make a zerodino ligand, so a 2-electron type of reaction. So we reduce the metal by 2 electrons. So this is what we consider to be electrophilic. Maybe easier to see with a phosphine. We can make the phosphinamine ligand here. We can also react with boranes to make this Lewis acid-base adduct. So formally, at least, there's no electron change here. It's not a non-redox reaction, so this is we consider to be a more nucleophilic type of reaction. We also see 1-electron reactions. So for example, with this compound, this is the dimer of triphenylmethyl radical. So this just couples with the nitrogen here to make an imido. And we can add this tempo H, which has a weak OH bond, and that makes ammonia and ultimately a tempo compound. Okay, so this is actually a lot of stuff we've done quite some time back. And so I just wanted to talk about some interesting reactions we found along the way, and then I'll talk about some of our efforts with different types of atomic ligands. So we were interested in trying to couple the nitride here with an NHC or stabilized carbene. And one interesting reaction we found was with this rather interesting molecule that doesn't look like it should be stable, but it's crystallizable. You can store it in the freezer in a solid state. The cyclopropylenine carbene. This reacts to actually make a cyanide ligand. So we remove the carbon atom from this triangular compound. We generate an alkyne, and we make a cyanide ligand. So this is a carbon atom transfer reaction. And then we can show by X-ray crystallography, and particularly by vibrational spectroscopy, we had the cyanide ligand here. And we were able to, we can actually isotopically enrich the nitride, and we could actually see the, for example, the CN ligand by NMR spectroscopy by N15 NMR, and this binds N2 reversibly. We can also use this to assemble clusters. So this nitride here reacts with this vanadium-3 complex and makes this heterobimetallic complex. The hope was to have some magnetic coupling, but actually what happens is vanadium is oxidized to vanadium-5, which is D0, so there's going to be no coupling going on there. But again, we can show by XPS, for example, that the vanadium is now vanadium-5 in this complex here. Okay, so actually just before the pandemic, we had this idea that maybe we could use the nitrides to make new ligands, new types of ligands. Since we know that they're amphiphilic, we can control reactivity in sort of atom transfer types of reactions. And so one target was phosphorus nitride, so PN. So this is, as you can see, is analogous to N2, NP2. But actually, PN is thermodynamically unstable with respect to the disproportionation to N2 and P2. So it's an inherently unstable molecule. Nonetheless, what's quite interesting about this was the first phosphorus-containing molecule to be observed in outer space. And amazingly, way back in the 1930s, PN had been detected in gas phase matrices at like 30 Kelvin, or actually lower than that. But once you warm it up, it oligomerizes or polymerizes. So there's many examples of using transition metals to stabilize things that are not particularly stable. So there were many examples of N2 compounds, there's examples of P2 compounds, but to our knowledge, when we started out, there were no examples of PN complexes. And so this seemed like an interesting target to go for, to try and stabilize PN as a ligand to a metal. So we would, again, people have tried this before, so the closest I think came was Kit Cummins' group, where they took this anionic vanadium nitride. This reactant here is designed to deliver a phosphorus atom once the chlorine is removed, so this will generate anthracene. So when they tried the reaction here, they actually get this trinuclear complex, where there's a triangle of phosphorus atoms that are created. But there was evidence for the formation of this vanadium PN complex, and then this dinuclear species in solution, although these were not observed or isolated, but based on the reactivity, these were inferred. And I'll just point out, subsequent to our work, Kit's group actually did isolate a PN compound by taking this N2 compound with this reagent that you can see is designed to eliminate N2 and anthracene, and that delivers PN to make an isolable compound. Okay, so this was not known when we started out. So the idea was, instead of using sort of these, well, at least from our perspective, exotic reagents, maybe we can just stick phosphorus and nitrogen together from two metal-containing complexes. And this is amazing because it's one of the few times that you propose a reaction and it works first time. So we used this isopropyl carbene ligand. There was no particular reason for using this one. We add this to this moly phosphide that Schrock made, and the only reason for using this is you can make this without using white phosphorus. And these two, if you mix them together, they make a new PN bond. So now this goes down to iron 2, and we have molybdenum 6, so it's now S equals 0. And so we could see by vibrational spectroscopy somewhere, oh yeah, here, that the stretching frequency of PN is a little lower than free PN, but more than in these matrices where it's believed it's coordinated in some way. So we could do this because we can actually isotopically enrich the nitride here with N15, so you can get both the N15 and natural abundance spectrum. And then the crystal structure here shows an NP distance of about 1.5 angstroms, which is comparable to gas phase PN from microwave spectroscopy. So this was pretty cool, but we were interested in trying to remove one of these metal ions so that we could make PN as a terminal ligand. And it took a while for us to figure this out, although we should have known the answer right away. So what's really important about this molecule here is this side, the iron is high spin. So metal ligand bonds here are relatively weak. And on this side, we have low spin molybdenum. The bonds here should be stronger. And we also knew that if you added a molecule that could make the 6 coordinate, it's going to go low spin, and it's going to break whatever bond is bound to the other. It's going to break this iron-nitrogen bond. It just took a while for us to realize we could do this. But if you add an isonitrile, then that's exactly what happens. So the isonitrile is a better ligand than nitrogen, and it's pretty slender. We can fit 3 of them in here. This is now a 6 coordinate diamagnetic compound. It's basically a non-coordinating cation, and we make this anionic moly PN complex here. So here's the crystal structure of the PN. You can see how actually massive our cation is in comparison. So we can get the phosphorus NMR of this complex here. So as I said, we can make the nitrogen here N15 only 50% because we make it from azide. And so if you do that, then you can see there's coupling in the phosphorus NMR, there's coupling to this nitrogen here. And if you don't have the N15 around, then it's a single line. Okay, now you may have noticed that I've showed, I hope, somewhat throughout that what the particularly relevant bond metrics are, but there's none shown here. And the reason for that is that it turns out this compound actually photoisomerizes. So if you leave this just stand in the lab, this will slowly photoisomerize PN, so phosphorus bound to molybdenum, to nitrogen bound to molybdenum. This was also kind of hard to figure out because in solution there was no evidence for any equilibrium. Presumably there's some very rapid isomerization. And so we did a single crystal experiment where we irradiated this complex in the X-ray diffractometer, and then in the dark we collected data, and then we irradiated again and collected data. And we could see that this slowly isomerized from PN to NP. If we look at the bond metrics here, so the PN bond distance is actually a little longer for the nitrogen-bound isomer. And if you look at the frontier orbitals, then the HOMO actually is a very nice back bonding orbital from a molybdenum d orbital into the PN pi star orbital. We don't know exactly how this works mechanistically, but if you try to flip this sideways using DFT, then the barrier is pretty high. So I'm not sure exactly how the isomerization works. So as I said, in solution looked like one compound. We wanted to get some evidence that actually we're doing this isomerization, and we tried to trap either isomer. So we thought that for this isomer, we have a very soft nucleophile. So this more likely will react with a soft electrophile. And then this would be more likely to react to something that's a hard nucleophile. So we took this rhodium-1 complex because it had a lot of phosphorus, so we hoped to see a lot of coupling that would help us to figure out what was going on. And if you add this rhodium-1 complex to this mixture, then you get mainly actually this complex here, but you also get a little bit of this. That's about less than 10% occupancy in the crystal structure. We can see this by NMR very nicely in the phosphorus NMR, so you can see. So the diamonds here correspond to the major isomer here with very nice coupling pattern, but then the circles here correspond to this guy here. And we could assign all the resonances in the phosphorus NMR for the major isomer quite nicely. Okay, so with all our success with nitride chemistry, we're interested in looking at other single atom ligands. An obvious target would be oxos. In fact, that was how we started out on this. We wanted to make oxo ligands, but we're never able to. So there's not many examples of iron 4 oxo where the ligand environment is a threefold symmetric. Here's 3 examples. What's notable about these, so these are iron 4. They're all high spin, in other words, where they have 4 unpaired electrons in them. If you add hydrogen bond donors in the second coordination sphere, it's possible to make iron 3 oxos. So the very first example of an iron oxo was actually this complex here from Andy Borovik's group. And what this does is actually attenuates the metal ligand multiple bonding here. So the bond length here is quite long compared to what you might expect for a double bond. And there's a couple of examples since then from Alison Fout and Theo Agapi. Again, these are all high spin complexes. So now it's iron 3, so there are about 5 unpaired electrons. Some time back, we showed that this tempo complex, which I showed earlier, if you heat it up, would eliminate an aminal radical that just reacted with solvent. Generally, we believed it was an iron oxide that could be trapped, for example, with the trityl radical to make this alkoxide complex. And so we knew that most likely we could form an iron oxo, but we just had to figure out how to get to there. And in the meantime, John Anderson's group at Chicago had isolated a cobalt oxo complex. And so we thought we should be able to get to this, and it's just a matter of figuring out the right reactants for that. And so the key, I think, was using this iron 1 N2 compound actually that Liang Deng's group in China first made. This reacts very nicely with N oxides. So here I'm using this N oxide to make an iron 3 oxo. And the crystal structure, again, is shown here. So you notice that the atomental groups are really, really big. The oxygen atom here is really hidden away in this pocket. There's no evidence of any hydrogen bonding from these atomental ligands to the oxo ligand, and so consequently the iron-oxygen bond length is much shorter than in the Borovic complex here. So we really think we have a true metal ligand multiple bond here that's not stabilized by anything else but metal ligand bond interactions. If you look at the Mossbauer spectroscopy, this is going to tell us something about the oxidation state and electronic environment. So we see the isomer shift, so that's the midpoint of this doublet here, is at minus 0.15 millimeters per second. That tells us something about the oxidation state, and we can compare with iron imiders we've made before that are also iron 4. This is very comparable isomer shift, so it's very consistent with higher oxidation state iron 3. And then if you look at the other iron oxos, they also have Mossbauer spectroscopy. And these isomer shifts are quite different, again, because they have a different electronic structure. These are all high-spin complexes. You notice that there's a small impurity in here, and I'll get back to that in a second. We know what it is. Since this is iron 3, and it's a low-spin complex, so it has one unpaired electron, we can show that by EPR. So the EPR spectrum here is most consistent with the unpaired electron in a DZ squared type of orbital, and that matches perfectly with the computed SOMO from DFT. So this DZ squared type orbital. So this is a very different type of iron oxo from any other iron oxo, particularly iron 3 oxo that have been reported until then. But nonetheless, it's still reactive. So I think the most interesting reaction it did was it can react with toluene. So it abstracts a hydrogen atom from toluene to make this hydroxide. This is the impurity we see in the Mossbauer spectrum. And what happens then is actually it can also couple with the radical to make some of the alkoxide complex here. So this is a sort of a different type of reaction. We also computed the bond energy. So the OH bond strength that's formed, we compute to be around 80 kcals per mole. It's much stronger than the bond formed from, for example, the Borovic oxo complex, which is around 64. And I think this demonstrates again how the hydrogen bonding network here really attenuates the reactivity of the oxo ligand here. So it decreases the OH bond strength for the hydroxide that would be formed. We could do one kind of catalysis reaction, not particularly interesting, I think, but if you use pyridine N oxide as your oxidant, we could oxidize some phosphines to the phosphine oxides using this as the catalyst. So we looked also at a series of substrates for understanding something about this hydrogen atom transfer reaction. So this is a sort of standard set of substrates here. So we can plot the relative rate of reaction for the hydrogen atom transfer reaction versus, for example, the bond energy for the CH bond that's been abstracted. So for example, for triphenyl methyl radical, it's a CH bond that's around 75 kcals per mole. And you see there's not really much of a correlation. I guess you could exclude this one and this one. You could imagine it's a straight line, but the data points are sort of all over the place. However, if you looked at the pKa of those bonds, of the CH bonds, then there's a much better correlation. So it appears that the mechanism of hydrogen atom transfer is driven by proton transfer. And that's very much like to what John Anderson saw from the cobalt oxo complex. So this is something we're still investigating, but we could look at just a square scheme to try and understand what's behind this. So if we think about a hydrogen atom transfer reaction, that involves the transfer of an electron and a proton. So you can break this down into a scheme where, so this is our hydrogen atom transfer reaction. So we can think about this as involving first electron transfer and then proton transfer. I guess we're actually going the other way. So proton transfer, then electron transfer. And so these are, in many cases, measurable quantities. So you can measure, for example, the potential for this electron transfer here. So we've done that. We could estimate the pKa here, knowing the computed bond energy. So this oxo here is relatively basic. And we could compare, for example, with the cobalt complex here. And so the cobalt complex, that we're actually able to measure the pKa. We couldn't measure the pKa directly, but it's, I think what this shows is that this is slightly more reduced, or the hydroxide here is slightly more reducing than the cobalt hydroxide here. And then another thing we could do is look at the rates of hydrogen atom transfer. So if we use dihydroanthracene as our model substrate, we can get the rates of reaction. So what was interesting was that the adamantyl cobalt oxide does not react in hydrogen atom transfer with dihydroanthracene, which was attributed to the large groups here. But we actually see a rate that's slow, but it's not zero either. But it's also not as fast as this cobalt oxo. And so I think the fact we see a reaction is not necessarily only due to sterics. And so if we look at since it's a proton-driven hydrogen atom transfer reaction, if we look at the structure of the iron hydroxide, that would be the first thing formed from proton transfer, then this is slightly bent here, whereas the cobalt hydroxide is very bent. So it's almost a sawhorse geometry at cobalt, whereas this is closer. And so our thinking is that the rate here is influenced by the reorganization energy that's required to get to this intermediate species here, which is much less for iron than for cobalt. This certainly would make this more sensitive to steric effects. And so again, this is something we still need to, we're still investigating. Okay, so this is oxygen. Can we do other elements? So sulfur is right below. Sulfur, of course, there's interest because of the iron-sulfur clusters in biology. So people have made what they called iron 2s clusters, if you can believe that, as a cluster, but a dinuclear complex with a single sulfur atom. Again, Andy Borovic made a sulfide complex, which is stabilized by hydrogen bonding. And then it's been proposed that a sulfide analog here would be a very good oxidant, and this is based just on computations. So again, not many examples of terminal sulfides for later transition metals. Sulfur, of course, is well known to form a lot of bonds to catenate, for example. But these examples here, these sulfides have been proposed as intermediates in reactions of different reactions. And only examples of stabilization are either through hydrogen bonding, as Andy Borovic showed, or Trevor Hayton has showed using alkali metals to cap the sulfide, so basically to quench lone pair character at the sulfide. So we thought maybe we could do the same thing. We have this very large adamantyl group. Maybe we can stabilize the sulfide. And this again worked first time. So if you add the right stoichiometric amount of sulfur, you can make the sulfide, and again we can crystallize this, a stable molecule. What was a bit surprising about this is if you look at the iron-carbon bond lengths here, they're much longer in this complex than they are in the oxo complex. So everything else is the same except this atomic element, and this is about a tenth of an angstrom longer. The iron-sulfur bond here is only it's also about a tenth of an angstrom shorter than in the Borovic compound, but not a dramatic change like we saw for the oxo. And the reason for this difference in bond lengths is actually the spin state here is different. So this is actually spin 5/2. So this is high spin iron 3, which is not best shown by the EPR spectrum, where the G tensors are consistent with 5/2. If you look at the Mossbauer spectrum, the isomer shift is quite different from the oxo. Remember that one was negative. This is now positive. We could also get the iron-sulfur stretch by using sulfur 34, and we could assign the stretching frequency of 470 nanometers. And just again to compare with the oxo, that the isomer shift here is quite negative in comparison to the sulfide. So we did quite a bit of computation to try and understand why this is a stable molecule. We can show from CAS-SCF that the high spin state is the lowest energy spin state by some amount. And then this is the dominant configuration. So we have 2 electrons in non-bonding orbitals. So for high spin iron 3, you have to have 5 unpaired electrons. We have this 1 electron in this pseudo sigma star orbital, and then we have 1 electron each in the pi star orbitals. And so if you think about this, this means we have half a sigma bond and then 2 half pi bonds that make up this iron sulfur double bond. And this is also supported by NBO. And so I think the ligand for sure helps to stabilize this, despite the fact we've actually quenched one of the metal ligand multiple bonds. This compound is still reactive, so we can also react with dihydroanthracene to make the hydrosulfide complex. This is a nice clean reaction. We can compute the SH bond energy of around 70 kcals per mole. It's very close to, it's very much like an organic hydrosulfide. And then if we look at the thermodynamics of this, so I think the only thing I really want to point out here is that this is a much worse, it's easier to oxidize the hydrosulfide, so this is a worse reductant. And so this is the major contributor to the fact that this is not as good at hydrogen atom, the sulfide rather, is not as good as hydrogen atom transfer as the oxo complex is. And then the rate is only about an order of magnitude slower for hydrogen atom transfer. And this actually does react with more sulfur. So if you add more sulfur, you get a disulfido complex here, which is now a spin 3/2. Again, from the EPR, the G tensors are most consistent with 3/2. It's a square pyramidal geometry. And what's surprising, I think, for this is that this compound doesn't seem to transfer sulfur atoms to substrates such as phosphines. And it doesn't do any other really interesting chemistry. Okay, so the last thing I'll talk about is carbides. So again, we had a long-term standing interest in trying to make these kinds of ligands. Again, the Cummins was the first to make for molybdenum this terminal carbide complex. So the only ligand on, or the only carbon is the only element in this ligand here. Since then, Tearapi has made a bunch of carbides on molybdenum. There's been a few examples, and I noticed that there shouldn't be an NH here, on these complexes that are related to alkene metathesis catalysts. And then Joe Templeton and Mike Hill have also stabilized carbides with alkali metals. So one of the challenges of making a carbide is it's not very good reagents for transferring a single carbon atom. So Kit Cummins' group developed this reagent, which is generated in situ. And so you can lose benzene. You form a methylidine that can be deprotonated. More recently, he made this compound. Again, you can see it's designed to lose N2 and anthracene, deliver a carbon atom. But this is an explosive compound, so that's sort of a reason not to use it. And then I showed earlier that this could transfer carbon to nitride to make cyanide. But apparently, that's the only carbon atom transfer reaction this reagent does. So we and also some other groups have looked at this, and there's other types of reactions that it does, particularly ring opening reactions that are not desirable. So one way you can make carbides is, and this is how the first example was made by deoxygenation of CO ligands. And so this has been attempted with iron, so Jonas Peters' group has become the closest. They can reduce CO with reductants, they can functionalize it, but then that's where they get stuck. CS has a weaker bond, and so this is often proposed as a way to make carbides. Again, in Jonas's group, they were unable to break the CS bonds. And then you could think about using ligands such as trimethyl diazomethane, which you could lose N2. You could probably desilylate with a fluoride source. But these, for Carson Meyer's group, and we've done similar chemistry, they only make nitride complexes. And it's not really a problem of the stability of the carbide. So way back, Mark Johnson showed that the bond strength here is reasonable and it should be an isolable molecule. So just a little bit about trying to do CO reduction. So we can make a monocarbonyl complex if we're very careful about controlling the stoichiometry of the reaction with CO. And if you add too much CO, you make the dicarbonyl. But if we try to reduce this, what happens is that we actually get insertion into the CH bond of the atom mantle, make this diamagnetic compound. This is an irreversible reaction. So this is not going to be the way to do it. So a couple of years ago, as I mentioned to some people, Jose Gorkachir joined our department, and we were interested in trying to use some of his chemistry for what we're doing, or use his reagents. And one of the things he's well known for is cyanide, so CP minus. They've developed a reagent to transfer cyanide. So if you compare cyanide with cyanide, it's a much better pi acceptor, and of course it's going to have a weaker CP bond. It does other things that cyanide doesn't necessarily do, so it can, for example, oligomerize. And it's another thing that's really important about cyanide is that phosphorus here is not particularly nucleophilic. So for example, if you try to substitute on rhodium with cyanide, actually the rhodium binds to the pi bond. And only when you block this can you bind another metal. So we were interested in looking at this for just paramagnetic complexes. So we can take either iron or manganese compounds with their cyanide transfer reagent. We can make these cyanide complexes. So we both have Raman spectroscopy, we have crystal structure data to demonstrate we make a cyanide compound. In terms of the cyanide ligand, these are very much the same as any other diamagnetic cyanide complexes. Okay, so then we were interested in trying to, actually we wanted to make a dinuclear complex where the cyanide would bridge to something that was paramagnetic, where we could look at magnetic coupling. And we chose to use the Cummins reagent, which is very good pi back bonder to do this. And we made some years ago a cyanide version. But when we take this 3-quartered moly compound with our cyanide compound, the first thing we were able to figure out what we made was the moly phosphide. And then eventually we were able to crystallize out this C2 complex, so this iron-bridged diacetylide complex here. So we again have a crystal structure, we have the Mossbauer, and then the Raman clearly shows we have a CC triple bond in this complex. So forming this suggests, well, obviously we have to break the CP bond, and you could imagine that you must be forming a transient carbide complex. So if you look at this reaction very carefully, at low temperature, you can measure a reversible equilibrium between the reagents, and what we propose is this compound here. And from the resulting thermodynamic parameters at minus 100 Kelvin, the equilibrium constant here is about 1. Again, this shows how non-nucleophilic this phosphorus atom is. But then as we warm it up, then there's enough thermal energy to drive the cleavage reaction to make the phosphide, and then this must leave behind a carbide. From DFT, we show the lowest energy spin state is spin 1/2, much like an iron nitride we made. And so this is the computed geometry is slightly bent at the iron because of the fact that it's Jahn-Teller active. We were not satisfied with that because maybe we've sort of convinced ourselves what's going on, and that's not correct. So we tried very hard to trap this, and finally we found with styrene we could actually trap the carbide. So we actually do the reaction in styrene as a solvent. So you mix these two in styrene, we again make the phosphide, and then we could isolate this carbene complex here that's formed from the the carbide. We still get a little bit of the diacetylide compound. So here's the crystal structure of this complex here. It has an interesting electronic ground structure where we have both iron 1, 2, and 3 resonance structures for this complex here. So it's kind of hard to make any other way, though. Okay, so just to bring everything together, so I think one thing we're going to be able to do in the future is just see how the nature of this single atom affects fundamental reactions or fundamental properties of reactions. And so one reaction, of course, is hydrogen atom transfer. And I showed earlier that for iron oxo, we can pull off a hydrogen atom. We go from low spin iron 3 to high spin iron 2. And then for the nitrides we looked at a long time ago, the computed first structure is actually low spin. And so what we find is actually the bond energy here for the OH bond is much stronger than this bond energy here. So we'll try to figure out what's behind these differences. And our working hypothesis, this is related to the covalency of the metal ligand multiple bond. So the more covalent it is, the weaker the resulting element H bond that's formed. Okay, so just to wrap everything up, so I think hopefully one thing you got out of this talk is that these bulky tris carbene ligands are a really great platform for making these metal ligand multiple bonds, particularly with elemental ligands that don't provide much steric protection by themselves. We can use atom transfer chemistry to assemble new ligands, and then we're looking at how thermodynamic driving force is related to the bonding properties of these complexes, particularly their covalency, which is going to affect spin state changes. So just to thank people who did the work. So a lot of this was done quite some time ago, but most recently, these two guys here did a lot of chemistry. So Jorge made the PN complex, Juan made the oxo and sulfido complexes. Dulika was the person who figured out or observed the first the reaction with the sulfide complexes, and Austin was able to trap the carbene complex. So for this project, we're relying on a lot of collaborators. So for X-ray crystallography, which is done in-house, EPR is done by collaborators, as is Resonance Raman, and also the Mossbauer, some of it was obtained at Ohio State. And of course, I need to acknowledge my colleague for providing sulfide, and then the funding agencies for supporting this work. Again, thank you for the invitation. I'll be happy to answer any questions you may have.
Thank you, Jeremy. We have time for some question. Jesus.
Very nice talk. Thank you very much. Super nice, fundamental single
Thanks.
atom chemistry. Really like it. I have a few questions. For example, because we have had some things at some point kind of similar with the sulfides and oxo. Do you never see the hydrogen atom transfer intramolecularly from your adamantyls or terbutyl groups in any of the cases?
We have not, but for example, let me see. I'm not going to try and mess around. So I think those bonds are too strong, but there's another ligand. So this isopropyl here, so this CH bond will be a bit weaker because it's adjacent to the nitrogen here. I think we've seen examples of hydrogen atom transfer, but I know for sure we've seen it with mesotyl. So with this substituent here, so we have a benzylic methyl group that's close to the metal center. We've seen hydrogen atom transfer from that. Yeah.
Well, you are safe once you are with the sp3 carbonyls in all cases.
So far, yes. Yeah, which means we're making not very reactive species. But yeah, for isolation is good. Yeah.
Nice. And for the carbide that you were showing at the end, did you make that also, or did you try to make that with the adamantyl one? Because I would assume that would avoid the acetylide formation.
Yeah, I agree totally with you about that assumption. Well, you can probably tell we've tried that. So there's a different problem that comes up. So this reaction doesn't work with adamantyl. Well, it does. It kind of works. So the student has done it. If you push on it hard enough, you get an equilibrium mixture of sulfide and halide. So he took the mixture and he added, that was good, and he added this reagent to it, but there was no reaction. So I think the adamantyl is just too big now. So I don't know what's between adamantyl and terbutyl.
You need also to design a smaller sulfide.
Yes, I think so. So with this one, if they back off on the sterics here, then they get like a oligomers of the like sci-fi bridges between metals. So I guess in retrospect, we were very lucky. We just had everything right. We didn't feel like it at the time. Yeah.
Well, thank you very much.
Thank
very
you.
Nice talk.
Bye-bye.
Following with that, have you tried smaller lithium crystalline volunteer?
Yeah. So that's something on the agenda. So we've tried the neopentyl, which I think actually has not been reported for molybdenum. But I think I have to think back. I think the student made it, or at least we believe we made it. But since I'm not reporting anything, it obviously didn't do anything of interest. The isopropyl 3/4 molybdenum is kind of challenging to make because it reacts very, very well with N2. And so one student tried to make it, but I think the issue was they're trying to make it on small scale. So if you look carefully at the Cummins papers, they make this compound on very large scale, and then they basically physically separate out the undesired nitride compound. And that's what we have to do. We just haven't done it yet. Yeah, so I think that's going to be our best way to solve this problem.
Any other question?
Yeah, nice talk. And for an organic chemist in the audience, you have been using so beautiful ligand.
Mm-hmm.
How difficult they are to do?
To make the ligands, they're quite easy actually. So we can make we can make imidazoles in like 19th century German chemistry, right? All in one pot, but we get like say 50% yield of the imidazole, and that's good enough. And so then to put the boron on, I don't have a good slide, but we use like, for example, you can use phenylborane dichloride. So that will just make a Lewis acid base adduct with an imidazole. But if you add like TMS triflate, then you can remove the chlorides and you can substitute the triflates by imidazoles. We make this dications. We can deprotonate with LDA. That step is sensitive to the type of base. It's not clear like what's going to work ahead of time, but once you figure out, it works very well. So we can make these ligands on gram scale easily, and the resulting metal complexes too. So that's another nice thing about this ligand system is that it's easy to make on large scale, relatively easy anyway.
Thank you.
So, really nice talk. Actually, I need to check the paper to make you the question because it was
Okay.
so much information my brain couldn't.
Yeah, I think I have too much in here.
Everything was pretty outstanding. So, regarding the oxo compound,
Uh-huh.
the iron 3 oxygen compound.
Yeah.
So I saw that you synthesize in THF.
Yeah.
And it reacts with a CH bond when you heat it up. So I guess that to generate such, like, the first question is, you think you could generate that iron compound by reaction with oxygen in a certain solvent?
We've
and
tried.
some reducing the compound and activating O2 or?
Yeah, so Juan first, once we had this, we were like, well, let's try to make it from O2. So if you take this N2 compound and I can't remember how much O2 you had, but you had stoichiometric O2, whether it was half or 1 equivalent, I don't remember. You got something diamagnetic, and we don't know what it is. He could never crystallize it. So we never tried it in the presence of another, what did you suggest, a reductant? We didn't.
Yeah, so you reduce the iron species
Yeah.
to make it even more active towards oxygen.
Yeah, the reaction with oxygen is not a problem. It's we don't know what we got. It's obviously not this because it's a diamagnetic compound. But I don't know what it is. Yeah.
Because it reacts with toluene when you heat it up.
Yeah.
You synthesize it in THF, and
Yeah.
I would be surprised that doesn't insert the oxygen in the carbon close to the oxygen of the THF. Like it doesn't react with.
CH bond in THF is stronger than that in toluene. So.
So it doesn't form a lactone or lactam or anything like.
Not that we can tell. I think this is pretty robust. I mean, so if you heat this up in benzene, you can heat it up to like 100 degrees, no problem for a few hours. Yeah. You see a lot of papers with iron oxides and the like where they use benzylic, substrates with benzylic CH bonds, and that's probably why they're easier to react. Yeah. Mm-hmm.
Okay.
Great talk.
Thank you.
Beautiful chemistry. I mean, I have just a curiosity
Mhm.
on one hand, and the other is about the mechanism about the MPN to MP isomerization. The curiosity is first, why, how do you came up with the idea to use lead to do this isomerization? And the second is, it seems that the isomerization via the eta 2 MP is quite high in energy. And I wonder if, did you consider to check if the silicon atoms around are playing any role on the ligand, assisting it, or something like that?
Okay, so your first question, yeah, so basically we're talking about this. So it's really hard to understand a photochemical driven reaction if you're not looking for it. So this is quite an interesting story, and it's one, I mean, in hindsight, at the time it was very frustrating. We had a very, crystallographers have a reputation of being very, attention to detail. So he was like that. And so, he could refine everything very well, except for PN, and you could refine better with, like, I think 30% NP. And we did this many, many times. Like, I think we had 3 or 4 crystals, basically the same occupancy. And so it's like, okay, well, I guess it's not that you're a bad crystallographer, right? But it is something real. But in solution, there was no evidence of a second compound. And so what we did was, the only time we were seeing this was on the diffractometer. So there's 2 ideas. One is that it's something to do with the X-rays, and the second idea is it's light. The student did tell me when he took this compound and just dried it off, it was orange. And then when he came back the next day, if he left it like just sitting in the vial, it was kind of a tan color. But that's like, who knows what that means, right? Maybe just desolvating. So then we did the crystallographer. I mean, it's an exciting experiment for the crystallographer because it's not just like this. It's not getting triphenylphosphine oxide. But so they did took one crystal, and then they did a series of experiments where they first did the X-ray radiation. So they covered the entire, and we don't have a setup for doing real photocrystallography. So they just covered every single light source in the room. They covered up the safety lights within the diffractometer. I'm not going to say which crystallographer it was. And then they radiated for some time with no data collection, and then they collected data, and they did like a few times. There was no change. And then they did the same thing. Then they exposed it to light, and then put it in the dark, and then collected data. And that's where we saw that summarization. That's when it has to be light. So that was, thanks to a very, careful crystallographer that it led to this discovery. So for mechanism, I don't really know. I don't know how we would test the silicons. I'd be interested to hear your idea on how you would test how the silicons are involved.
Yeah, I was wondering, I mean, if you change the silicon by, I don't know, you can prepare by terpothyl or something like that. Does it change something?
Maybe. So one really big problem with this project is that all the experimental stuff was done by the end of 2019, early 2020. And then, well, something happened in 2020. And then the student graduated. And so all the momentum of this project went away, unfortunately. So we haven't really gone back to this, which, yeah, there's, I think, a lot of stuff we can do. We could actually, he was able to, so this is anionic, actually, right? And we actually did get one crystal structure where it was oxidized, but he could never reproduce that experiment, the synthesis of that. And that was something else I was interested in looking at. So we've actually, in a sort of serendipitous reaction, we've made the PN bridge compound with the Cummins tris analido. And so I think we're going to try get back to that somehow. We have to figure out how to make the tris analido phosphide without using white phosphorus, because white phosphorus is just like, yeah, you can't get it anymore. Yeah. So it's not really an answer to your question, I know, but yeah.
I mean, it's a hard question.
Yeah.
Mm. Okay.
Thank you.
So we can finish here. Let's thank again Jeremy. Thank you.